In weak acids and weak bases, they're a little trickier compared to strong acids and strong bases. And so you want to pay attention to the nuances between the two, and you should be able to identify what is a strong acid or a strong base versus what is a weak acid and a weak base. So we're going to be doing all these calculations with weak acids and weak bases. So this is just summarizing all the things we're going to be doing. And so first we're going to go behind the theory of the stuff on the constant equation sheet that you use on the test. And so let's talk about weak acids first. So you can see here the weak acid is HA, that's the generic form of the weak acid, and then it is in equilibrium with water. And so when water is there, the weak acid could give a little bit of the hydrogen away so that it becomes hydronium and the conjugate base. As a reminder, if you have weak acid, you have conjugate base. If you have a weak base, you have a conjugate acid on the other side. So make sure you follow along with those things. So again, this is the weak acid and this is the conjugate base. And so technically, we can also have the conjugate base act like a base. And so it could grab another H from water, since water is part of the solution as a solvent. And so you can make the weak acid and a hydroxide as you see over here. So you want to be very, very careful. That conjugate base can react with another water molecule instead. So there's technically both equilibriums happening at the same time. And so it's not strong. The conjugate base is not strong. It's still acting like a base though. So both of them are weak. Okay, so we have a weak acid and we have a weak conjugate base. So make sure you know that both of them are technically happening. And so in this solution of weak acid, well, we have the weak acid, which is HA. We have hydronium, the H3O+. We have the conjugate base, technically, because it exists. But remember, not all of it ionizes completely because it's a weak acid, so we're still going to have HA in there. It's just a little bit will, change. And so as a reminder, if you know the concentration of a weak acid, that does not mean you know how many H pluses or how many hydroniums are in solution. You can't get the pH directly, and so you have to do the more complicated math compared to what we learned in a previous section. And so I can write the Ka value as you see here. And so it is based off the first highlighted part, the original generic form right here. And so you have the hydronium, the conjugate base, and then the weak acid. pKa, power of Ka, remember that power of anything is just negative log of that. So if you know this, you can calculate pKa very easily. And so if you have a higher Ka value, that means you have more product, aka if you have a stronger acid in terms of relativity to other weak acids. As a reminder, this is still weak compared to a strong acid because a strong acid will ionize completely. A weak one will just, ionize a little bit. And so again, more products is this. If I have hella of this guy, that means we're, decently strong, but again, relative. Cool. And so if you need to calculate the percent ionization for seeing how strong something is in general, we have this equation down here. And so it's pretty much just comparing how much ion of H plus you have, or H3O plus again, tomato, and how much of the concentration of weak acid there is, and then you multiply it by 100, and then you can just calculate that. So very similarly to weak acids, we have our weak bases. So we're going to have the same similar-ish situations happen. So the weak base is just represented with a B. And so the weak base can act like a base. So it's going to grab an H from water. And so we have its conjugate acid right here. And then we have hydroxide being formed. And so as a reminder, the conjugate acid can act like an acid, so we could donate that H to water in solution, and so now we have the base and hydronium. So we have all those players, okay? So we have our base, we have our conjugate acid, and we have our hydroxide. So again, not all of the base is going to accept the H plus, so we'll have that excess of that guy, okay? And so just like with weak acids, weak bases, you can't get the concentration of OH minus, and so we can't calculate pOH directly, and so we have to do the math. We use Kb values, and so we have the conjugate acid, again, conjugate acid, be careful. Then you have the hydroxide concentration and then base. pKb is just negative log Kb, just like any other p value. So from the previous unit, we can apply it to this unit. So again, higher Ka, stronger weak acid, as I mentioned earlier. If I have a higher Kb, then we have a stronger weak base. Again, this is all relative. And so we can compare these relationships with the conjugate acids and bases. So again, this was mentioned the previous slides ago, where we have our Ka and our Kb, and we can use those, right? And so we have the acid, conjugate base, and so I could technically multiply them together. And so I can have a bunch of stuff cancel out, just because, you know, up and down, you can cancel stuff out. And so I have my hydronium and my hydroxide, and then I multiply it together, and then I get that equation. And so on our constant equation sheet, you can now know that Ka times Kb is Kw. And so we can use the values and calculate whatever we need to calculate. So, cool. As a reminder, water isn't in Ka or Kb because it's a liquid. And so here's our constant equation sheet from earlier. And so here we have our Ka now for our weak acid, we have our Kb for our weak base, and now we have the Kw equals Ka times Kb. So we use those two things to get that. Again, this is theory, you don't need to necessarily know this. Okay, so now we can put the things we learned to practice. So here is a practice problem. And so we're at room temp. We have a weak acid, we have a conjugate base, and we have a Kb value. And so ionization constant, how do we do that? So pretty much we're just trying to get the Ka, because we're talking about a weak acid. We know information of the conjugate base, so we can derive some stuff from that information. So I'm going to go ahead, and you could see here I wrote down the equilibrium for the weak acid. So I removed the water step. Again, you can include the water step if you'd like. So you would have the weak acid plus water, and then the equilibrium symbol, and then H3O plus, and then the conjugate base. I just skipped that step, but again, you can have that on there if you want to, because again, you'll just have hydronium, which is what College Board prefers. And so I can use this equation that's on our constant equation sheet, and so I can reorganize it a little bit to solve for Ka. Kw is a constant at room temperature, and if we had a different temperature, then I would need a different Kw value, but since it's at room temp, I'm going to go ahead and put that on top, and then Kb, what was given in the problem, and then I was able to calculate Ka just from doing the simple math. So nice, easy peasy. Cool. And so conceptually, I could check this math. Like, I could do all these math problems, but you know, sometimes you mess up on the math, and so you can think about how this relates conceptually. And so we see the Kb value is higher, and so the conjugate base is a stronger base compared to the weak acid. Again, they're both weak, but because of the value of Ka that was calculated versus the Kb, we know that the conjugate base acts way more like a base compared to the acid acting like an acid. Again, they're both weak, it's just that Kb is bigger, so therefore will act more like a base. And so Again, Ka value shows how it's going to donate its H to water or to whoever. And so remember, it's products being formed. So we're thinking of what things are being made. And so Ka being such a really, really low number, 10 to the negative 11, it's not going to really produce that much product, again, compared to Kb. And so we could see these values here. If you're like not sure based off 10 times 10 to the whatever, I have written it out so you can see the Ka is super small compared to the Kb. Alrighty, second problem. So what's the pH of that solution of acetic acid? And so we have a Ka value, we have a concentration, and so we're going to calculate some stuff. And so if you know acetate ion, then you should know what acetic acid is. If you don't know the acetate ion, then here. So the acetate ion is this part right here, and so when it's an acid, you just throw an H on there, or however many H's you need to balance out the polyatomic ion, and then you got it. Now in this problem, I showed it with water. Again, you don't have to, but College Board prefers it, and so I'm putting water here. And so I give the H to water, and so it becomes hydronium, and then we have the acetate ion. And so I made a little rice table just to make sure that I know the information given in the problem and be able to calculate stuff. Now, remember, water is a liquid, so we don't fill out that section, but we fill out everything else. We don't know how much equilibrium is going to happen right now, and so that's why it's X. We started at nothing. And so we have to see how much equilibrium action is going to happen. We have the original solution of this, and we're going to see how much is going to be used up in order to make products. And so, just like with the previous unit, can I do the shortcut? So you take the K constant, multiply by 100, and you compare it to the reactants, concentration in this case. And so I have my K value right here. I plug it in here. And so yes, indeed, the shortcut works. And so I can round this to be about 0.075 to make the math faster. As a reminder, if you don't do the shortcut, the math just takes longer, but you'll still end up getting the algebra regardless. And so because the X is going to be so negligible, we round it to be about that. And so we're about that concentration. So I'm going to go ahead and we just plug in our values. So we have our Ka value, which I plugged in here. We have our X's over here. And so those get multiplied together. We got X squared. And then we got 0.075 on the bottom. Do some simple math where we multiply this on both sides. And then we're going to square root because there's a X squared here. And so I end up getting the 0.001162. Now, does that actually solve our problem? We read the question again. We say, hey, look, it says, what is the pH? We just solved for X, which is just the concentration of H3O+. And so we need to do a little bit more. And so it's asking for pH, not the concentration of hydronium. And so we have to do the other step, which is to take this concentration, and then we plug it into the pH formula that's on our constant equation sheet. And so it's just negative log that concentration, and I get 2.93. And so sig figs for logs are really, really weird. The first digit, as I have bolded here, doesn't count. I'm not going to explain why here, so if you're interested, you can go back to the slides and click this, and then you can read about it, but I'm not going to go over it. So we have 2 sig figs, because this was 2 sig figs up here, and so these are the 2 that count. All right, next problem. So what's the pH of this solution of ammonia? Okay, we got ammonia this time. And so I'm going to go ahead and set up ammonia as such. So it is acting like a base because it is grabbing an H from water. And so now we have the ammonium ion and hydroxide ion in the product side. And so Just like before, I'm going to set up the rice table. Again, water is a liquid, so we don't include that in our rice table. We could just ignore that part straight up. And so then I want to make sure to check the shortcut. So KB is 1.8 times 10 to the negative 5. If I multiply that by 100, it's going to be negative 3. And so it ends up being okay to do the shortcut. So I can go ahead and round that last E part on the ammonia to be about 0.25 because that X value is going to be so small after calculating it. So I set up my KB just like how I did the previous problem. I have my products on top and my reactants on the bottom, and then I am just plugging in stuff. I have my X's on the top, I have my 0.25 on the bottom, I do algebra, and then I get my X value. Cool. Now, this one is different. This one's asking for pH. In the first problem, or the previous problem we did, we calculated H3O plus concentration, but in this case we have the hydroxide. So we have to do a couple extra steps. So you want to be very careful. So this asks for pH, not hydroxide, right? And so I have the hydroxide concentration, so I can calculate POH because I don't have H plus directly. So I can calculate POH. I got it as 2.67. And then I can go to the other equation on our constant equation sheet, which is pH plus POH equals 14. So I go ahead and plug in POH there, do some subtraction, and then I get 11.33. So this required 2 small extra steps afterwards. So you want to be very mindful of that when you are calculating stuff. What is the question asking for? Did I get there yet? Or do I have to do multiple steps? So this next problem is actually going to be really interesting because in this example, we have something that dissociates completely, but has an ion that can act like a base, as I've set up here. So what's the pH of the solution? We have a Ka of a weak acid, but in the question, there is nothing mentioning a weak acid at all. So we need to think this through. So first, we're making a solution, right? We have this Kf, and imagine you have it as a solid. You are dissolving it in water, so there should be a H2O on top of this arrow. And so we have our aqueous ions chilling in solution. As a reminder, there's that one solubility rule you have to memorize. Then potassium was one of those ions you had to memorize. So we knew this dissolves completely in water. And so since that solubility rule is a thing you memorized, right? We know this already. Cool. And so the thing about this is technically we have F minus. F minus can be made using water. So water can act like an acid to F minus. So that's going to act like a conjugate base. It's going to grab an H from that water. And so technically, we are making the weak acid HF, and we have the OH minus. So technically, that is happening in solution. This is very important distinction. Ka is given, but why am I doing Kb, right? So we have Ka given because we have a weak acid, and a weak acid is there because usually that's what you have. But the F minus, the fluoride ion, is acting like a base. So we need to do stuff with Kb. And so since I know Ka reflects a weak acid separating to its ions, or you can have the weak acid reacting to water, and then you have hydronium and then F minus. So I could look back at the equation we wrote earlier, so the one up here, that doesn't match that. Not at all. And so, again, it's acting like a base. It's a conjugate base. So we need Kb to calculate hydroxide to then get H+. And so we could take the equation we learned earlier, the Kw equals Ka times Kb. I could solve for Kb by moving stuff around. We always assume everything's done in room temp, which is why I make the Kw the constant that we already know. And so then you should just plug and chug. And so you can see here, we assumed again all the values are at 25 degrees Celsius. If not, we would need the value for kW because you would not know it otherwise. So we had to do an additional step in this before doing other stuff because we had to think, what did the equation look like and how did it relate? Okay, so we're going to set up a rice table for this, okay? KF dissociated completely, and so we technically have the initial concentration of fluoride ions. Everything's 1-to-1 because KF dissolved completely. In this equilibrium, we have the F minus that is just 1 coefficient, so everything's nice and easy for that part. And so I'm going to go ahead and set up my rice table as I did. Again, water is not part of it because it is a liquid. And so we have our different values here. So again, we don't know the values of the hydroxide or the weak acid. And so we're going to go ahead and put those at 0. And then we have the initial concentration of F minus because that, again, that was given in the problem earlier. And so now we can set this up. First, we can check if the shortcut works. And so we have the KB we calculated on the previous slide, and it indeed does. So we're at the point where this should be doable for you, and so you should be able to do the rest of this problem. Again, it's set up for you on the example paper, so try it out first before you move on. So go ahead and pause this video real quick. Okay, so again, we have our rice table. We have this shortcut, so we rounded that there since x is negligible. Again, if you didn't notice the shortcut, the math is the same. It's just slightly more complicated because you have to deal with more x's and yada yada. Okay, so I set up my KB because this is acting again like a base. And so we have our weak acid, we have our hydroxide, and then we have our base. And so I'm going to go ahead and put those in. I have the KB we calculated earlier. I have my x squared on the top because they're both x, and then 0.15 because again we can round, do some simple math, and then we end up getting our x value. So we end up getting that guy. But the question was asking for pH, not pOH minus concentration. So we're going to go ahead and do those equations just like the previous problem. So I have my hydroxide. I'm going to go calculate the pOH by plugging it into negative log OH. And so I get that value. And then again, I use the same equation as I mentioned earlier. The pH plus pOH is 14. And so then I plug and chug, and then I get my base. But wait. What if you have a strong acid and a strong base, right? So let's say it was KCl. Okay, so KF was the problem I just went over, but what if it was potassium chloride instead? So let's say we're dissolving it, right? So we have the KCl, we're dissolving it, K plus, and then ACl minus. Great. Now, this is technically a conjugate base of a strong acid. Remember the strong acid list you had to memorize? So hydrochloric acid is one of those strong acids. And so, as a reminder, strong acids completely dissociate. So, because it completely dissociates, as I have shown here, you're never going to make HCl. So Cl minus is not going to make HCl. Again, HCl is a complete dissociation because it's a strong acid. So Cl minus is not going to do the opposite and make an acid eventually. Like, it's not going to happen because, again, it's a strong acid if it were to try to act like a base. So KCl won't change the pH of a solution because, again, it is the conjugate base of a strong acid. Again, you can't make a strong acid, so it's not going to change it. KF does because F minus can, again, act like a base. It could grab an H from water and become HF, but Cl minus cannot grab an H from water because, again, it would be producing HCl, which it won't because it is a strong acid, HCl is. So be very careful about that. Okay, nitrous acid. So if nitrous acid has a Ka value of that at 25, what's the percent dissociation of nitrous acid? So I set up my reaction as I do here. And so we have our water. The water is acting like a base. It is getting an H from the nitrous acid. And so now I have my two ions on the right side. And just like always, we set up a rice table. The water doesn't count because that water is a liquid, so don't fill out that part of the rice table. We were given an initial concentration of the nitrous acid, and so I set up my rice table. Now, the shortcut works. Again, always check. But if you don't, the math will be the same math, just slightly more complicated. And so in this case, it works because you could see I just plugged it in. You could see the math right there. And so finish the rest of this problem. Again, it's set up very similar to the previous one. So go ahead and pause this video and try it yourself first before I talk about it. Alrighty, ready? Here we go. So we have our Ka value. Our Ka value was that, so I plug that in. These two are x's, so I got x squared, and then this was rounded, so I got 0.4. You multiply both sides by 0.4, square root both sides, and then you get your answer, your x value. Does that solve the question? The question asks, what is the percent dissociation? I got an x value. That's not percent dissociation, so you want to make sure you plug it into the correct equation. And so percent ionization, aka percent dissociation, here is our equation we got earlier. And so you just plug in the stuff. We have H3O plus here, we have our nitrous acid here, and I multiply by 100. So I have how much H3O plus ends up being in solution at equilibrium versus what was the initial concentration of the nitrous acid to compare to. And then I end up getting 3.2% dissociates to this. So notice it's a weak acid. Not a lot of H3O plus was made, and that makes sense because the value was so small. The percent is so small. So again, you just want to be careful with what the question is asking for to know what to plug and chug. If you want to be more mindful about the percent ionization, we have this sentence that I've highlighted here. And so we can say that 3.2% of the nitrous acid dissociated into those ions. That's just a formality answer. You don't necessarily need to write that unless like you weren't clear on what you were plugging into an equation, because some of y'all don't know how to show your work. Alrighty, here's your turn. So try it out yourself, see if you can calculate it, and then start the rest of this video. So go ahead and pause this video first to see if you could do this yourself. Okay, ready? Here we go. So we have the first parts here. First, we have our rice table. We set it up just like usual. We have our equation. The liquid doesn't count, so we don't include the water. So you just want to be mindful of that. And so then we check if the shortcut works. The shortcut does work, so I'm going to go ahead and round the reactant to be about 0.667. And then we just plug in into our Ka. So our Ka is our products over reactants. We were given a Ka value, and then I just plug in the x's and I plug in the products, and then we math, and then we end up getting this x value here that I have highlighted in yellow. Now, we solved for the H+, but the problem says calculate the pH. So you put pH equals negative log of that H+, and then we plug and chug, and we get our pH. So that is the first part. So the second part was calculating the ionization percentage of vinegar. And so we go ahead and plug into our formula that was given earlier. So we have our equilibrium, H3O plus, and then our initial weak acid. And so we just go ahead and I put the ions here so you know which one is which. And then I just plug in the values here. And then we see this amount of vinegar is its constituent ions, the ions that form vinegar. And that's it for this section. The math is pretty easy in this section because it's just, using rice tables as we've done before, using a new Ka and Kb. But again, we've talked about equilibrium constants, so this one shouldn't be too shabby. So you just want to be very mindful about the shortcut, whether it works or not, because if it doesn't work, then you have to do a little bit more math, but otherwise it's not too bad. Alrighty, see ya next time. Bye!